to achieve, large differential mode voltage gain. Okay, so in a differential mode voltage gain is we may have some negative sign. Driver transconductance GM2, GM3 plus all those arrow things. Yeah. So if I increase VDD prime, then my GM3 will increase, right? GM3 will increase. So, yeah, sometimes, yeah, if I increase VD3 properly, this transconductance can be 0. The load resistance can be infinite, right? Yeah, we can adjust that by using LC oscillator. Our LC is something like that. We need a gyrator, right? If we have a gyrator thing is here, say I have a GM thing here, and then I have a capacitor there, okay. Then this looks like a inductor, right? This is inductor. GM square over C, C over GM square, I'm not sure. Which is which? L over C. Yeah. C over GM square. Is it right? Yeah. I think this is good. Square root L over C is a impedance. It should be 1 over GM. So, yeah. See, I want have an LC oscillator, something like that. Okay. Then, see, I can put C there, right? If I put C here, then I have a LC, this LC resonant circuit, okay? If you put capacitor there, then it doesn't actually, yeah, we should put capacitor there, then we have a LC parallel circuit. So we want to emulate this, actually what's this gyrator looks like? Gyrator is nothing but I have a GM thing here, and then see this is plus minus plus minus something like that, right? Say I have a capacitor here, and then I have another GM here. Let's just see. Yeah, it should be connected. So I'm looking. I'm actually let's draw a single-ended version. Say this is a plus plus. Is this plus plus? Yeah. And then I have a C there, and then I have another one, plus minus or something like that. Right? Yeah, this is my gyrator, right? GM. I have a non-inverting transconductor and the inverting transconductor. What's the differential version? The differential version of this gyrator can be, yeah, I have a differential version. Then I have a capacitor here, okay? And then I need let's just see. Is this the one? Let me see. Let me check the circuit. Okay. Let me redraw this thing. Plus minus minus plus, okay? And then so this is my input, and then here I'm crossing this thing to generate Actually, this is a non-inverting version. Plus, minus, minus, plus. Okay. And then this thing is connected to there. Say, if I put capacitor here, yeah, this is my LC resonator. So we'll see inductor here, okay? And then we have a parallel capacitor. Yeah, so for this, actually this is my nota cell, okay? So I will adjust the VDD prime for the GM3 to sustain oscillation. So if my output resistance, you know, GM2, GM3, and then all those resistance, if this resistance, this conductance becomes 0, then the output will have some oscillation, right? It has some, frequency is dependent on GM over C. Just frequency is actually square root LC. Oscillation frequency is like that. Okay, you know, this inductor is only GM, C over GM square, right? Times, let's just see. This is a C, right? Oh, yeah. Okay, so my oscillation frequency will be GM over C, right? Okay. If this thing becomes positive, then oscillation will die out, right? Die out. If this thing is negative, oscillation will grow with the time, right? And then it will saturate the somewhere, and then it will saturate the sum at the supply voltage. So when for the proper VDD prime value, this becomes 0 and will have some constant amplitude oscillation, right? That's a Q tuning. We can adjust this GM by using some phase-locked loop to set oscillation frequency to a fixed frequency. Okay? So we have two kinds of tuning circuit. Question? No question? Okay, let's repeat a little bit about this VCM generator for another. This is another version of inverter-based amplifier. So for this inverter-based amplifier, this is not nota cell. So, you know, in a nota cell, common mode is controlled by a cross-coupled inverter, right? This cross-coupled inverter. Yeah, this one controls to fix some common mode, right? Yeah, but in the second version, we want to use, let's just say, we want to use those two inverters in parallel, but we want to control common mode by some different means. See, for example, yeah, this is BIP, BOM, BOP, BIM. Say, we take just a common mode output, use a differential amplifier, and then put some, this thing is some connected to some logic threshold, something like that, okay? This is a logic threshold, okay? And then we can use inverters like that, okay? to control common mode. So then this should be negative, positive, right? So this part is a CMFB circuit, right? This is in the nota cell. This is a kind of CMFB, right? A kind of CMFB. Actually, there is another thing. This bias. This is still complex, right? So in a nota cell, common mode gain is pretty large. It can be larger than 1. Okay, that's no good. But in this scheme, my common mode voltage gain can be pretty small. Then let's just see, what is my differential mode gain? For the differential mode gain, yeah, this is for DC, so it doesn't drive. Differential mode gain can be just GMD times that arrow thing. This can be arrow 2. GM2 arrow 2. I don't know whether you can apply this one here. Say you can apply this one here to increase common mode gain or with a CMFB. Okay, I didn't try yet. So this is the second approach. So for this second approach, there are 2 kinds. See, I can adjust this VDD to set, by using a resistor. Okay, so for this second version of this pseudo differential